Hello, everyone, and welcome to the final talk of our international conference. It's been an incredible event, but this final talk promises to round it off quite wonderfully. We are joined by Dr. Jill Tarter of the SETI Institute, who will be donating to following the talk, so she can continue her research. She is a pillar within SETI and the scientific community, having received many awards and accolades. And as I say, it is an honour to have you with us. So please, Jill Tarter, take us away, please.
Thank you, Eden. I'm very pleased to be here, and I think that we're successfully sharing my screen for everyone. So I will get started, and I'm going to try and change your perspective today and broaden it beyond what might be your what you wake up in the morning thinking about. And so I'm part of a team of astronomers who use astronomical instruments to try and answer this really old question of, are we alone? And we recognize that although the acronym SETI stands for the Search for Extraterrestrial Intelligence, we can neither define intelligence nor do we know how to find it directly. So what we do is try and use our observational capabilities here in this 21st century to see if we can find evidence of someone else's technology at interstellar distances. And in doing this, I think that it's really important to have a concept of how large this search might need to be successful, admitting up front that indeed the answer to the question might be that we are alone, that we are at least practically unique. So I'd like to start by having you think about what we mean by here and now, right? So let's start with the question of here. So for me, like most of you, that means I'm working on a laptop at home, right? That's what the coronavirus has given us. And in my case, that particular here is in this house in the Berkeley Hills in the San Francisco Bay Area, right? And if we could take a look from the altitude of low Earth orbiting satellites, my here would be on the western coast of the United States. And in 1968, astronaut Bill Anders took this Christmas Eve photo of Earthrise. And it was the first time that we were able to envision ourselves on a planet floating in the blackness of space and to see our home from this particular perspective. And I think it changed fundamentally how we see ourselves, and it became an emblem for the environmental movement, right? So in the summer of 2013, the Cassini spacecraft that was orbiting Saturn turned around and looked back and made this selfie of us, right? At the end of that arrow, there's a tiny white dot, and that's us. That's all of us. Hopefully you got the memo and you went outside and looked up and waved at Cassini when this picture was being taken. But that's who we are, that's where we are. That's a version of here. And earlier than that, in 1990, the Voyager 1 spacecraft was at the distance of Neptune, and it was about to leave the solar system, and it turned around and it captured this iconic pale blue dot in a sunbeam. And that's us, that's here. And now we understand that our sun, is nowhere near the center of our Milky Way galaxy. And in fact, we are only one of something like 400 billion stars in this beautiful spiral galaxy. And until now, I've shown you actual photographs taken of us, but this is an image not of our Milky Way galaxy because we can't get outside of it to look back and take this image. It's an image of a galaxy called M101, Messier 101, which we think is a good analog for our own Milky Way. And until recently, we couldn't verify that because in optical wavelengths, you can't even see the center of the Milky Way galaxy because of the dust in the interstellar medium that scatters and absorbs visible light. However, indeed, not at optical wavelengths, but at radio wavelengths, you can see into the center of the Milky Way galaxy. And so last year, for the first time, as a result of spending something like 5,000 hours of radio telescope time mapping gas and dust in the Milky Way galaxy, CO and hydrogen, we indeed were able to map the Milky Way galaxy from the inside out. And you can see that it sort of looks like that. I mean, we were pretty close. But now we know what our galaxy actually looks like. And this is what it would look like if indeed you could get outside the galaxy and look back. And not only do we now appreciate that our sun is one of only is only one of about 400 billion stars in the galaxy, we understand that our galaxy is one of something like 200 billion galaxies in the observable universe. So our here is given in this Hubble Deep Field image, where we see that the points of light are not stars, but individual galaxies. And some of them are smaller and fainter than others because they are farther away. And this reminds us that as we look farther and deeper into space, we're also looking farther back in time, which means that we need to think about what we mean by now, right? And our now is the current epoch of cosmic evolution from the origin of the observable universe about 13.8 billion years ago. And this is essentially a scientific creation myth. And it is our best model of how we think our universe began and evolved. And there's much that we don't understand. We're actually only able to observe about 4% of the matter energy density in the universe. And the rest we call dark matter, dark energy. Means dark just is a code word for we don't know. We actually don't know what it is. We can measure its impact and its influence because of the gravitational force that it imparts on other objects that we can observe. But back at the very earliest times, we can do pretty well at telling this evolutionary story. But at the earliest times, we cannot yet make quantum mechanics and gravity play nice. So we can't yet have a good mathematical model for those very early instants. But this is the most self-consistent perspective of here and now that we've been able to assemble. And we can expect that it will be subject to change in the future as our physics and mathematics improve. So we humans are actually intimately connected with all of those faraway events in space and time, because we trace our lineage not just back through the centuries of our families, not just back through the millennia of human civilizations with its art and its many experiments with different types of governance. We humans trace our heritage not just back over the millions of years since we branched off from the great apes, and not just back over the 2.4 billion years during which the Earth's atmosphere has been perfused with oxygen thanks to the photosynthetic labors of cyanobacteria. We humans trace our lineage not just back to the formation of the sun in our solar system 4.568 billion years ago. We have to go back farther, millions of years, to a giant molecular cloud that was contaminated by the winds of Wolf-Rayet stars and the debris from supernova explosions, such as this modern one that I've pictured here. Indeed, the iron atoms in the hemoglobin molecules of your blood, and the calcium in your bones, and all the elements heavier than helium that make you, they were all fused long ago, deep within massive stars that ended their lives in catastrophic convulsions, leaving behind remnants such as this modern example. Remnants that became incorporated into our early solar system, just as this modern supernova remnant will be incorporated into future generations of stars and planets and perhaps life. So over the 400 years since the invention by Galileo of the telescope, we have come to appreciate the fact that it actually takes a cosmos to make a human. It's true that you are literally made of stardust, and we continue this exploration because we are interested in understanding who we are and why we are and what else might be out there, and of course, who else might be out there. So we're on this journey of scientific exploration to find our place in the cosmos. And so over my own career, there have been two incredible game changers that have altered the course of that journey. And that those game changers are extremophiles and exoplanets, right? Extremophiles is life as we did not know it until a few decades ago, thriving in places that we once thought completely hostile to life. At least that's what I was taught when I was a student. But these extremophiles are now illuminating the amazing possibilities for life on our own planet and perhaps elsewhere within our solar system and out into the cosmos. And then today, thanks to the Kepler spacecraft and ground-based observations, we can say with statistical certainty that there are more planets than stars in the Milky Way galaxy, and there is thus potentially much more habitable real estate out there than we might have ever imagined. And certainly that was a possibility when I was a student, right? So this is really, for me, extraordinarily exciting. So we are thinking of all kinds of different missions that could perhaps allow us to search for life beyond the Earth. And what we'll be able to do is going to be strongly influenced by the results, at least in our country, in the United States, strongly influenced by the results of the decadal survey that has just been completed. And we would like to be able to image distant exoplanets and do a spectroscopic analysis of their atmospheres to look for disequilibrium chemistry, the kind of chemistry that characterizes the Earth's atmosphere. So in our atmosphere, as in no other atmosphere of any other body in the solar system, on Earth, we have in our atmosphere large amounts of molecular oxygen and methane gases. And these are very reactive gases, and you put them together in the laboratory and they instantly turn into carbon dioxide and water. Nevertheless, we have observable amounts of these gases in our atmosphere, and the reason is because we have biology on the surface of the planet. We have plants and trees photosynthesizing and pumping molecular oxygen into the atmosphere. And we have bovine flatulence, cow fart, giving us a large dose of methane. So these biological source functions on the surface of the planet provide the opportunity to have disequilibrium and measurably disequilibrium chemistry in the atmosphere. And we'd like to look at atmospheres of other bodies to see if we can see this sort of thing. But it's going to be a difficult job to do. First of all, the measurements will be difficult to make. And secondly, the analysis of the measurements will be tricky because they will not necessarily be unambiguous, and they may require a lot more contextual information about the history of the exoplanet that we are observing that we might not have. I mean, for example, just recently, much closer to home, we've seen the claim of the detection of phosphine in the cloud layers of Venus, and potentially the claim that this means that there's biology associated with the cloud deck in Venus. Now, there are a couple of problems here. First, the detection is a single line detection. So we think it's phosphine, but it might not be. We might have gotten the wrong molecule. And second, in order to say, this might mean biology, we have to be able to say we've looked at extensively and exhaustively at all of the chemical networks that could possibly take place to produce this gas. And we find that that none of them are capable of producing phosphine without some biological interaction, as we find on Earth today. So here's a world much closer to home than an exoplanet, and we are looking at a potential biosignature, but we're also scratching our heads because it isn't a smoking gun, and we don't actually have any smoking guns. So biosignatures are really worthwhile trying to find, but they may not give us an absolute yes or no answer. So that leaves us with the opportunity to look for technosignatures, which might be less ambiguous, right? So what we're trying to do here is to look with the technologies and the physics that we currently have to see if we can find evidence of someone else using technology on a large enough scale so that it will have impacts on its environment that we could perhaps sense over interstellar distances. So that's what SETI is. It's really a search for technosignatures. So it uses the tools of astronomy to search for evidence of someone else's technology in the universe. We might not necessarily know what that technology is being used for, but if indeed it is detectable given our own telescopes and 21st century technology, then we might come up with a less ambiguous set of observations that imply that there's technology being used, and from that infer that at least at some time there were intelligent technologists who created this technology. Right? So historically, we started using radio astronomy, radio telescopes, to look for signals from intelligent technologists. And then we expanded it into the optical domain to look for signs of someone else's technology, and then into the near infrared, right? Because optical observations are limited by the scattering and absorption of dust between the stars. So the near infrared has a farther reach. And what we're looking for is something that is obviously engineered and not natural. So this is what we call a waterfall plot. Frequency is plotted on the horizontal axis and time on the vertical axis. And each of those dots indicates the power above threshold of a single individual, very narrow frequency channel in a small time unit. And you can see that most of that snow, right, is noise. Actually, 10% of it is actually coming from the galaxy, the rest from our own internal instruments. But there are clearly a couple of things in that plot that are not noise. And this is the way the planet Mars looks to our narrowband spectrometers when the Mars Express and Mars Reconnaissance Orbiter are on our side of the planet and transmitting back to the Deep Space Network. So this is the kind of thing that we've been looking for over decades. Something that is obviously an engineered signal versus something that is natural. And in the radio, we have concentrated on frequency compression, looking for signals that are narrower than nature can produce. And in the optical domain, we've been looking for time compression, very, very short signals that we don't think nature can produce, but lasers can do so easily. So in order for SETI to succeed, two technological civilizations are going to have to be close to one another in order to be detectable. And we need to remember that that closeness is not only in space, but in time. So for SETI to succeed, two technological civilizations have to overlap in time in the history of our 10 billion year old galaxy. So that's not going to happen unless technologies on average have a very large longevity, unless they last for a long time. So we're a very young technology in a very old galaxy, and we don't know yet whether it's possible to become an old technology. But if SETI succeeds, then indeed we know that it's possible to grow old. And so Philip Morrison liked to refer to SETI as the archaeology of the future. It's archaeology because of the tyranny of light speed, right? Any information that we receive will be telling us about their past. But the fact that we do receive such a signal means that it's possible for us to have a long future. So if somebody else made it through this technological adolescent phase that we find ourselves in, then we can too. And for me, that's the real reason to work on SETI, because there are so many other indications that we in fact might have a short and not a long future, that I really hope to be able to find a reason to say, no, in fact, a long future is possible. And that would be the detection of someone else's technology. So we've been at this for 50, well, for now, 60 plus years. And when SETI turned 50, I did a calculation that said, okay, how big is this search we're trying to undertake? And it's actually 9-dimensional, right? You got 3 spatial dimensions. You have time as a dimension, 2 senses of polarization, modulation schemes that will affect your ability to detect a signal. And lastly, sensitivity. We don't know how strong a transmitter might be and how far away it might be. So we don't really know how sensitive we need to be to make a search. And I took that 9-dimensional volume, and not being very good at imagining 9-dimensional volumes, I said, okay, let's just say that volume is equal to the volume of all the Earth's oceans. And how much have we searched? Well, in 50 years, the answer was that we had searched 1 glass of water out of the Earth's oceans. Now, a couple of years ago, 60 plus years on, the students at Penn State redid the calculation and they find, well, it's more like a small swimming pool's worth of the ocean that we've sampled. Means there's a lot to go yet, right? So we've done a lot more searching, but there's certainly a lot more to go, which is why, let me try and forestall a question later on, which is, there is no Fermi paradox, right? The answer to the Fermi paradox is there's no paradox, because we just haven't looked far enough and well enough to be able to say they're not here. So we've got a lot of searching ahead of us, and it's very encouraging that we're seeing exponential growth in our ability to search and the speed with which we can search. So I'm excited by what the future holds. And in Northern California, in partnership with the University of California, Berkeley, the SETI Institute built a new telescope called the Allen Telescope Array. It is the first time that we built the equivalent of a large radio telescope by hooking together a large number of small dishes, right? We had hoped that it would be 350 dishes, but indeed, after we got some funding to do this, we realized that we still had a huge amount of technology development ahead of us. And so by the time that we actually finished that and figured out how to make this thing work, we only had funds to build a much smaller number of dishes. And if you're not going to get to 350, where should you stop along the way? Well, it seemed to me that if 42 was the answer to life, the universe, and everything, then that was a good number. And so that is what we have today at the Allen Telescope Array. And silicon is as important in this array as aluminum and steel, right? There's an enormous amount of computing that's required to collect the output from all of these telescopes and phase it up and then look for signals coming from a particular direction on the sky, or in fact, from multiple directions, because we actually can phase it up a number of times to form different beams on the sky simultaneously. So that's the Allen Telescope Array. And today, probably the biggest search that's underway is funded by Yuri Milner and the Breakthrough Initiatives. And they have promised $100 million over 10 years for this expanding this search, and they're about halfway through it now, and they didn't build their own telescopes. What they're doing is using other telescopes around the world and building exquisite signal detection back ends for these telescopes. And they have a search protocol that wants to look at all the stars within 5 parsecs of the Earth. They want to, they have a target list of 1,000 stars that span all spectral types. And they want to also, with lower sensitivity, search 1 million nearby stars. They want to search the central regions of at least 100 nearby galaxies. And then, of course, any exotic objects that come along, such as Oumuamua. So both the Allen Telescope Array and the Berkeley group observed that object, all of us having grown up on science fiction and remembering Arthur Clarke's Rendezvous with Rama. It seemed like an obvious exotic object that we should take a look at, and we didn't find any reason to think that it was technological as opposed to astrophysical. But we wrote the papers and published them, and any new exotic objects that show up will go on to our observing list. So Breakthrough is currently built back ends for the Green Bank Telescope in West Virginia, for the Parkes Telescope in New South Wales. And you may have seen the publication recently of Breakthrough Listen Candidate 1 signal. I wouldn't pay any attention to that. The protocol that was being used when these observations were taken was not the specific SETI protocol, and they really don't have a good filter for interference in this way. So I'm not impressed by it. If I had been running the project, you would never have heard about that signal. And I don't know who it was that talked to the Guardian, but anyway, they're observing at Parkes. And the kind of thing that we're looking for, right, is a pattern, a particularly well-defined pattern. So I showed you some examples earlier, but if you look at this waterfall plot, there's actually a signal in there. And by now your eye may have found it, but once I point it out to you, you can't fail to see it. There it is. And it's a huge, to our algorithms, it has a very large signal to noise ratio. So this is what our computers have been told to look for. And the thing that I find really exciting is that right now, with the emergence of machine learning and neural networks, we're at a point where we can transition to not just asking our computers to find this kind of narrowband pattern or the short optical pulses, but in fact, to tell us whether there's any information contained in our data or whether it is just astrophysical noise. So I'm really excited about the opportunity to have more sensitivity to different kinds of modulated signals, and in particular to transients. So in Breakthrough Listen is also using this planet finder detector at Lick, an optical telescope, and they have made memoranda of understanding. Well, with both with the large FAST telescope in China, with the Meerkat telescope in South Africa, and with the Jodrell Bank telescope and the Merlin interferometer in the UK. And so they will be building backends for these telescopes to include or to improve their coverage. And they look to be on track to complete their observing program and protocol within the next 5 years. So there's more SETI telescopes, right? Until, sadly, just this past few months, we could have told you about the SETI that was being done in a commensal way at the Arecibo telescope, analyzing data that was taken for other observing processes, for observing programs for SETI signals. But sadly now we've lost Arecibo and we don't know what the future will be. In the UK and across Europe, there's something called LOFAR, low frequency array, that's being used to look for low frequency transients for SETI. There's a group in Italy and Medicina using this telescope to look for SETI signals. And down in Southern California, NASA took one of the Deep Space Network telescopes and moved it outside the fence at Goldstone. And now there is the Goldstone Apple Valley Radio Telescope, which is a fantastic outreach and teaching facility. And so the students at Gabbard are actually doing a sky survey to look for SETI signals. And in Western Australia, the Malura Wide Field Array has also been used to look for low frequency SETI signals, although that's not the reason it was built. At Harvard, they analyzed the optical sky visible from Harvard, Massachusetts, a number of times, looking for optical SETI signals on a telescope actually built by the students. It's also possible to take data from the high-res spectrometer on the Keck telescopes in Hawaii and analyze them and reanalyze that data looking for engineered as opposed to astrophysical signals. There's an amateur optical observatory in Panama that is looking for SETI signals. And lastly, oh no, not quite lastly, here's the near infrared facility at Lick Observatory that's being built and used for finding SETI signals. And lastly, it is possible to do archival SETI, that is, to take data from spacecraft or other observing facilities that have been collected for other reasons, such as the infrared survey of the entire sky by the WISE satellite, then looking to see if there's evidence of an infrared glow from a Kardashev type 2 civilization, which has built something like a Dyson sphere to capture all of the energy from its star. And the backside of that structure would glow in the infrared. And then if you even take that farther to consider all the stars in your galaxy having done this kind of astroengineering, then you can look for so-called Kardashev type 3 civilizations in the data from WISE. And a team at Penn State has done that kind of analysis. So in the near future, in optical and infrared, first of all, there's a set of 4 telescopes in Arizona called Veritas. It's used to find the air showers from high energy particles entering the Earth's atmosphere. So without building any new hardware for that telescope, but simply writing new software that says, I don't want to find a shower. I don't want to find a whole bunch of my photodiodes lighting up along a trail. I want to find in each of those 4 telescopes a single pixel that lights up from the same piece of sky. So Veritas is now looking for SETI signals that way. There's a telescope that's being constructed in the University of California, San Diego, called Panoceti. And this idea is to build something that looks like Buckminster Fuller Dome. Here is another picture of it. And filling each of those hexagons in the dome with a Fresnel lens that images a large patch of the sky onto a small photo detector, and thereby building a telescope that can look at 10,000 square degrees of the sky at one time. And of course, in order to be able to claim some kind of validity to any sort of transient signal, you need to build two of these telescopes, these observatories, in the northern hemisphere and have them co-observe the same patch of 10,000 square degrees on the sky. And then you also need to build two more in the southern hemisphere in order for you to see all of the sky. But that is underway, not fully funded, but it is underway. And then there's a second project being done at the SETI Institute, which instead of using Fresnel lenses and photodetectors, uses very high quality cameras with gratings and very fast readout times. And with the installation of 8 cameras at about a dozen sites around the world, you will actually be able to observe all the sky all the time for transient signals. And oops, sorry, didn't mean that one. Let's go forward. And the first of these observatory sites is in Northern California in Sonoma at the Ferguson Observatory. And the next one, we've been sitting here waiting for COVID and quarantine regulations to lift because it will go to Mauna Kea in Hawaii. And then again, not fully funded, but eventually we hope to have these facilities around the globe so we can actually be watching all of the sky all of the time. And then we think about what the astronomical community is doing in the future. So JWST is hopefully finally going to launch this year. And then after that, there will be other facilities. And we need to figure out a way to observe commensally with these telescopes. That is, we need to be able to make copies of the data and process them for engineered versus astrophysical signals. So following JWST, we're going to have the Roman telescope and perhaps a star shade. And then following that, Habex or Louvois or whatever the decadal review suggests. And it is imperative that we get smart enough to figure out how to co-use the data from these new telescopes. Here's a telescope that's been suggested by a group in Hawaii that has only one purpose. The only thing this telescope can do, which looks more like a radio telescope than an optical telescope, is to image the Proxima Centauri system. And if we could watch and detect the light curve from hundreds of orbits of Proxima b around its host star, it would be possible to deconvolve those intensity light curves to make an opacity map and actually tell the difference between continents and oceans on Proxima b, and indeed do an analysis for biosignatures. No idea whether the astronomy community actually has the appetite for such a single mode telescope. In the past, we've built telescopes that are something for everyone, and we'll see what happens with this very clever idea. Of course, we've got the 30-meter telescope and the Giant Magellan Telescope and the European Extremely Large Telescope and the Large Synoptic Sky Survey Telescope in the planning stages or about to become operational. And again, we need to figure out how we can put instrumentation or how we can make copies of the data coming from these telescopes in order to look for engineered signals. Then we've got Panoceti and LaserSeti that we're thinking about and trying to make operational. And then the large Chinese Fast Telescope and eventually the Square Kilometer Array Telescope, where studies for the cradle of life, or SETI, are actually in their science case. And so we have to build instrumentation for these instruments. Perhaps if the decadal recommends it, we can expand the Very Large Array in Socorro, New Mexico, and have the next generation VLA telescopes, and we want the data from those. And ultimately, if that Exo Life Finder telescope, that funny Ferris wheel kind of looking telescope, can be proven to work, we could build something based on the idea of phasing up individual optical services, something 80 meters across. Colossus is what it's called. And this would actually be able to find the heat signatures of cities on distant exoplanets. Don't know whether this will ever come to pass. So I think that in addition to forcing new instrumentation innovations, I think SETI has another extremely important purpose. I think that when talking to groups like yours, talking about SETI, thinking about SETI, trying to change your perspective about here and now, has the effect of holding up a mirror to all of us on this planet that says, look, compared to something else that may have originated and evolved on a planet around another star, even though superficially in that mirror we might look different, we are actually all the same. We are Earthlings, all the same when compared to something else out there. And I think that's really an important message, because we have all these challenges, problems that we need to solve in the near term, challenges that don't respect national boundaries and that are going to require global cooperation to get there, to find solutions. And I think the more that we can see ourselves as Earthlings, the more that we can adopt this cosmic perspective, the better we will be at solving those challenges. And so the last word actually comes from Caleb Scharf, who's the chair of the astrobiology department at Columbia University. And Caleb reminds us that on a finite world, a cosmic perspective isn't a luxury, it's a necessity. So indeed, at this point, I usually give a homework assignment to the people that I'm speaking to. And that assignment is, when you get back to all of your devices, and these devices will have a profile that explains who you are, I'd like you to go in and change that profile so that the first thing you say about yourself is that you're an Earthling, and then act like it. Okay, thank you.
Wow, thank you so much. And I think that's a wonderful way to round it off. It's such a powerful message, especially at the in the current circumstances with COVID, which is a problem that is being faced by the whole world, and we're having to try and deal with it together, sharing vaccines and everything. And yeah, no, thank you so much. It's also incredibly exciting just to think that, as you say, there's so much space that we haven't explored yet, or haven't searched yet, and also that the world is working together, as you say, people coming together from all parts of the globe to search the night sky. So I think that is incredibly exciting. So thank you so much for sharing that with us. Any questions, please put them in the chat. There are a couple here already. So someone's asking, what would be the first step, say if you did detect some technological signals, what would be the first steps in possibly trying to communicate with whatever life is out there, or what would you do once you found these signals?
Well, first of all, for any discovery site, the next step for them would be to get an independent verification, right? To have somebody with equipment that they didn't build and software they didn't write verify that they can see what it is that you think you've seen. And then you tell the world. And in terms of communicating back, there's something that we wrote ages ago, back in the 1980s, called the PostDetection Protocol. And there's a bullet in there that says that, and there's no enforcement for this document, right? But scientific organizations that were working on SETI voluntarily signed it. And it said that that no one should transmit a reply until there was a global consensus that we should, and there was a global consensus on who should speak for Earth and what we should say. And that sounds great. We didn't know how to get global consensus back then. We still don't, but that is the philosophical high ground, right? That we shouldn't just go ahead and anybody who has a telescope shout back and say whatever they want. On the other hand, Freeman Dyson used to say to me, well, come on, Jill, get real. If you announce the detection of a signal, that's exactly what's going to happen. Anybody who can transmit will, and they'll say whatever the heck they want. And then he said, and wouldn't that great cacophony be about the best description of the 21st century Earth?
That is a good point. I mean, how would we communicate? What kind of signals would we send back?
I think probably the simplest thing is that whatever the form of the detection that we make, we simply copy that and return it, right? Because we know that they will have equipment that can generate that kind of information bearing signal, and so they can most likely receive it.
Yeah. Someone else is also asking, is any research being done at SETI as to what extraterrestrial life would look like? And if not, is there any such research going on in the world that you know of?
Well, the SETI Institute has the name SETI, and so you think that that's what we do. Everybody is searching. But indeed, at the SETI Institute, I think the last count was we have 111 PhD scientists who are working on all aspects of life beyond Earth, all different phases of astrobiology. And some of them are trying to figure out how life could be made in different ways. For me, I've just always skirted that subject because I know that what I can detect is potentially evidence of someone else's technology. I don't care what they look like. I don't think they're going to be microscopic or microbial in scale because I don't know how you build large enough transmitters to be detectable if you're that kind of entity. But really, I don't care. I'm looking for technology, and if we find evidence of some other technology, we're going to infer that at least at some time there were intelligent technologists that created it. So I've always just skirted that question my whole career.
And of all the new developments being made at SETI, which of them are the ones you're most excited about?
Well, I'm very excited about the new telescopes that are being constructed and our ability to observe commensally with them. But I am actually extremely excited about this idea of machine learning and neural networks, because we have been searching for precise patterns in frequency and time for decades. Those might be the wrong patterns. We might have been doing an exquisitely good job at looking for exactly the wrong thing. So I am excited that machine learning might give us the opportunity to simply say, here's the data. Is there anything in here other than noise?
Yeah, no, that is exciting. Oh, and some more light-hearted questions. What's your favorite fiction about encountering aliens?
Well, I kind of like the movie Contact, but beyond that, I really liked the movie Arrival, because I'm fascinated by the thought that if you have a language that writes in a circle, you have to be able to know the future. I thought that was a very clever idea for a movie.
Awesome. Well, thank you ever so much for coming, and as I say again, for sharing all your research with us. And yeah, it's been pretty inspiring, and I think anyone here will go away and probably do a bit more reading around the subject. So thank you ever so much.
Well, I hope so, because we've got to train our replacements.
Okay, and thank you everyone for coming and for asking questions, and engaging in all our talks. And also a shout out to Chaos's president, who has been alongside me in all these talks and has kept me going. So thank you, Orlando.
Eden did all the work. Thank you very, very much, Professor Tarter.
Well, I hope that you do this again next year with a lot of success.
We hope so too, I'm sure. Thank you.
Yeah, thank you so much.
All right. Bye-bye, you guys.
Bye.
Bye. Enjoy the rest of your day, and everyone else, enjoy the rest of your evening.
Well, congratulations, Eden. Awesome stuff.
You okay? You're not tired yet, are you?
Oh my God, I'm so tired. Yeah, no, I'm gonna go have dinner.
Yes,
let's
go.
have a chat, a meeting maybe after the one on Friday, sort of summing up sort of what went well, what didn't. Maybe we could get Ailish and Will along to draw from their experience as well. But again, thank you so much.
No, thank you. Okay, right, go have your dinner. You must be starving.
Have a good evening.
You too.
Bye.
Bye.